So I will talk on an extremal problem in Fourier analysis. And this is based on two joint works with my colleagues down here. And I apologize to people, especially from the BECAM, who may have heard part of this talk some months ago. But I will try to present something also a bit new for them. So what's the problem that I'm interested? I think this is, in a sense, a basic problem in Fourier analysis, is that you are just considering functions which are band limited. So that means that the support of the Fourier transform is in the interval minus pi pi, and I'm asking what's the smallest constant such that the evaluation is always a bounded, the evaluation at the origin is always a bounded linear operator, and I'm asking which is the norm of this operator in the polynomial. So the norm that I'm taking is an LP norm. Yeah? So I'm taking LP norms, if you want, LP of R whose Fourier transform is in minus pi pi. Good. So I would like to know not just, of course, the best constant here, the norm of the bounded linear operator, but also the extremizers. Which are the extremizers? Which are the functions that achieve the norm, if they do, and if they are unique or not. So, well, equivalently, you just take a function in the polynomial space, which has value 1, and you want to minimize the LP norm. So this is we are asking what's the norm of this embedding. Very good. So that's the question that I want to address. And let's do a warm up with the easiest case. No, the easiest case is when p is equal to 2, and when p is equal to 2, of course, this is a space of entire functions. No, the L function which have supported the Fourier transform is supported in an interval. It's band limited functions are entire functions of exponential type whose restriction to R is in LP. But if in the case of L2, they have the structure of a reproducing kernel Hilbert space. So any function f, by the way, the value 0 is just for convenience. I could have taken any real point because the problem is invariant under translations, of course. So f of 0, of course, it can be reconstructed by the integration against the sinc kernel. If you take Fourier, you take Plancherel here, this integral is the Fourier, and this is just is the identity minus 1, 1, of course. So that formula is trivial. And therefore, by the Cauchy-Schwarz, we get that C2 is smaller than 1, but you can apply it to the sinc itself, you get that it's exactly 1. So here you have that the unique minimizer is the sinc, in the case when p is equal to 2. Phi sub 2, by this I denote the minimizer if it's unique. Well, here the structure of this extremizer is that well, the zeros are all simple and real. They are the integers, and the goal is to understand the constant and the extremal functions for all p beyond p equal to 2, which is the trivial case. Good. So why do we care? Okay. So here there is a list of people who have cared about this problem. And there are two cases that show up that have been attracted more attention than others. That's the case p equal 1, and this was this was studied. I think that it's fair to say that before this work, the more advanced work that was done on the study of the problem itself was done by Hormander and Berhanson in 1993. Where they were studying some Bohr type inequalities for the Cauchy-Riemann operator. So this is, if you want, so inequalities for the gradient, but only for the d-bar of. This problem shows up in analytic number theory studying the gap between primes. So this paper by Carneiro, Milinovic, and Durajan, 2019, and they got this. They needed this estimate, the C1, the constant C1 was needed to get a good estimates for the gap between primes. And the best results that they use the results of Hormander, they invoke the results of Hormander to get them their best results. Now, there is this problem on operator theory that the norm of certain matrices, which are Hilbert type matrices, the norm of these matrices in certain space of operator depends on the C1 norm and some characteristic of the points, or some geometric characteristic of the points that are used to construct these Hilbert type matrices. This, in the theory of, if you want, of orthonormal polynomials, there is some similar constants which were studied by Levin and Lubinsky, and they prove that they scale as the degree goes to infinity, they scale to these CP constants. So in the theory of orthogonal polynomials, these constants appear asymptotically as natural spaces. Also, as some Nikolsky constants for trigonometric polynomials, the embedding of one LP in another Q in the torus, for instance, the best constants are related to these CP constants on approximation theory and so on and so forth. Now, the case P equal 4 shows up in additive combinatorics. I mean, there is, and this I will not treat, but this I can leave as an open problem. So let me show you this work by Ben Green. Ben Green has a list of 100 open problems, and there is one of them that for one particular range, it coincides with the C4, the case P equal 4. I mean, let me tell you what's this problem about. This I have to. So here he has a function f, say in L, I don't know. It's a function in L1, if you want, of minus 1/2, 1/2, and he wants such that the integral of f is equal to 1, and they want to minimize the you take the convolution. I mean, you think of this as a function in R, defined in the whole R, but supported here in minus 1/2 and 1/2, and you take the convolution, and you want this to be minimal. Well, that's the self-convolution to be minimal. The problem that they wanted to study some sort of size of certain Sidon sets in additive combinatorics, and this is related to the case that you want this to be the L infinity norm, to be as small as possible. That's what you would like. The L infinity norm of the self-convolution to be as small as possible. But this is apparently a very hard problem, and they only have upper and lower bounds, which do not match at all. And then they relax the problem to work with LP norms, which seems easier, right? And the best results that they got is when this, the case P equal 2. The case P equal 2, so this is the problem. You have a function in L1 with integral 1, you want to minimize. This question. So that's the question that shows up in this additive combinatorics, to minimize this as a relaxation of this one, which is the hard one. And this, of course, if you take F to be the Fourier transform of this condition this condition is just that f of 0 is equal to 1. So this is normalizing this, and this thing by Plancherel, this is L4. You want to minimize. So among the Pauli-Wiener functions, because f is a Pauli-Wiener function, the Fourier transform is supported in an interval. With norm 1, you want to minimize the L4th norm. So this is what I'm saying, that the L4th has been studied. Well, there are upper and lower bounds, but it's still not clear what's the structure of the minimizer little f, or if you prefer, the structure of the minimizer of its Fourier transform. So this also appears here. And if you take any other p here, it will not match this other problem. These are two scales of problems. They match at the case p equal 2 corresponds to the case p equal 4 of this other one. Good. Well, somebody cared. That's the only thing. Now, what's the situation in general? Okay, for any p between 0 and infinity, well, the solutions of the extremal problem exist. This is just a question of compactness. You just you work in this. There is a compactness argument for this sort of for these polywinners spaces, so that's no problem. They have only real simple zeros. This is already non-trivial, but well, when p is bigger than 1, okay, when p is bigger than 1, in the range strictly bigger, then just by the strict convexity of the norm, it's easy to check that the solution is unique. So there is a uniqueness. For p equal 1, this requires a proof. But for p bigger than 1, it's trivial. And therefore, you can, if you have a function in the polywinners space, you can symmetrize it, right? And it will be another solution. So when you symmetrize it, I mean, you consider this one. This will be another entire function, which is, and therefore by uniqueness, you check that f should be real on the reals. So the extremal is real on the reals. The zeros a priori are either real or they appear in couples reflected through us, but you can rule out the fact that they are, so they are all in the real line, and they are, you can also prove that they are all simple. So at the end of the day, well, and of course, the solution, I can also reflect it with minus zeta, so it's going to be an even function. And so we know that the solution is going to be an even real function, and the zeros, therefore, will happen in couples, Tn and minus Tn. And since it's a function of exponential type, in this convex range, we have that the extremal function can be written in terms of an infinite product of the zeros, this entire function. So if you want to describe the extremal function, you can as well describe the zeros, and you are done. Well, you have this infinite product. Okay, good. So now, well, of course, in the case of the p equal 2, you will just Tn will be just the integers, and then this will be. Now the reproducing form, and this will be the sink. Now you can do. So you want to minimize the LP norm among functions that have value 0, 1. So you can as well, you compute the Euler-Lagrange conditions, no, for the minimizers, and the fact that the function is a critical, this is what it gives you. So you have a reproducing kernel for a general P, so that the value at 0 is going to be, for any function in the polywinner P space, you can write it as f of x times this, well, this is just the constant, and here you got phi of p divided by the modulus of this to the power of p minus 2. And this is essentially, it's the only, there is only one critical point, which is going to be fp, phi p, sorry. So you want to find out which function phi is such that when I take the modulus and I construct this thing, you get a reproducing formula. So for p equal 2, this thing just, well, for p equal 2, this doesn't show up. This is just the usual sink, the reproducing formula that we had before. And the case that p equal 1, you can see already that it's a bit special, because when p is equal 1, this thing here, well, this is a constant that goes out. So this thing here really is just the sign of phi 1. So this is the sign of phi 1. It only takes value 1 and minus 1. So in this reproducing formula, you get that any function f of 0 is the integral of f of x in some intervals and minus f of x and some other intervals. So this reproducing formula, you can see very clearly that the zeros play a role very clearly here in this thing, because it determines everything. The zeros determine the reproducing formula. So far, so good. Very good. Now, I tell you what Hormander and Bernhardsson did. They did some incredible piece of work, taking into account the conditions that they had, especially computer-wise. They got C1 nailed to this digit. You see, this was 19 and 20. But as they claim in their paper, unfortunately, we could not identify the extremal function using the numerical data. But this is rigorous. They prove this rigorously, just up to the. But they couldn't identify the. And this is the extremal. How do you call this? This is the reproducing formula that I was telling you about. Concentrated. I will concentrate now here. From now on, in the case p equal 1, from now on. So this is this is the formula that I'm. So phi, I will just write phi instead of phi 1. So that's the stream of gears here. Well, so our goal is to fulfill the program of Hormander and Bernhardsson, that is to describe the properties, the structural properties that the extremal function has, and to nail down what's the right constant here. That's our objective. Very good. Well, now that's a spoiler because I'm drawing already the picture of the solution. That the phi is going to look something like this, and if you observe, this thing looks like the zeros are very close to the half integers, except that if you look closely, they are slightly shift towards the origin, slightly shift towards the origin, but very close, and they get closer and closer to the half integers. Looks a Bessel type function. Well, to be honest, I have this numerical data, and I know that there is a Bessel function that approximates very well, and I superimposed it, and you cannot distinguish. You can say that this is as well a Bessel function, but still it's not. But it looks very much. And if you do this, we can prove rigorously that the picture looks like this. If you do the case p bigger than 2, then this will move. The zeros will just go away towards. They will move to the right. Okay, but this is something that we don't know. That the zeros behave monotonously with p. That they shift monotonously with p. This is something we conjecture, but this is not. Okay. What the case p equal 1 is special? Well, this I'm telling you, this depends only on the sign, therefore the zeros, but also because we can try to write down what's there is this other function which in a sense looks close to our, this is our phi. Phi is the sign of phi, well, normalize it, is the sign, that's the one that we want to nail down. And this is capital phi, and this is psi. And this psi is the sign of cosine of pi x. So the Fourier, this is a periodic function. Therefore, if you look at its Fourier transform, it will vanish in minus pi pi. It will be supported only on the integers, no? And the convolution, well, you can check it's in phi t. Now you see, phi is extremal. Now I'm losing the. Okay, let's go back. Let's go back to this situation. So the fact that this is extremal means that I have this reproducing formula. If you look on the Fourier side, this function phi of x lives on the interval minus pi pi. Now, if this means that the projection of this, that means that this function, the Fourier transform of this function in the interval minus pi pi should be a constant. So I have the reproducing formula, so that this is the identity. So morally speaking, so the condition is that the projection of this function, phi pi is in the Pali-Wiener space, but when I take the modulus of those, of course I kill the holomorphicity. But then when I project back into the holomorphic space, I should recover the sink. I should recover the sink. So the condition is that the projection of this onto the Pali-Wiener space, which means the convolution with this with the sink, should be the sink. And that's what I brought here. The convolution of this with this capital phi with the sink, this phi 2 is the sink, should be the sink. And I can safely subtract this psi here. I can safely subtract this psi here because the Fourier transform of this one is vanishing on minus pi pi, so this doesn't affect the equality. So phi is extremal if and only if this is equal to phi 2, if and only if this is equal to phi 2. Doesn't matter. Okay, but now the point is that I can check out the thing that I subtracted here is because it kills part of the growth. So I can prove that this thing is going to be in the Pali-Wiener space. And to check that this equality holds, these are two functions in the Pali-Wiener space, P2, in the classical. But a function in the Pali-Wiener space, it's the uniqueness set are the integers. So I can just put this thing, this equality onto the integers, and I will get a system of equations. And you write this down, and this horrible system of equations. So this thing, now you look, tau n are going to be the zeros, of our extremal function. So as the picture shows, they are very close to n plus 1/2. So I just look at the difference. This difference should be small. And now, well, you impose the condition, the Euler-Lagrange equations, and this translates on this system of equations. This is this system of equations that should hold for all the integers. Well, only the ones to the right because the function is even. So I just have to take care about this k1, 2. So I have to impose this system of equations. Well, this is just a matter of solving this linear system of equations. The incognitas are the delta n, the shift of the zeros. So I have to solve this system of equations. Well, and you can do, this is like the linear part of this equation. You linearize it, and now you have to invert this linear infinite matrix. You do it, and you prove, okay, with a standard application of the fixed point theorem, that there is a solution, tau n, assuming that the L2 norm is bounded by 0 to 13. So that means that we did in a previous work. So that means that we can prove that there is a solution, and the solution, the location of the zeros are really going to be, as we showed in the picture, they are going to be little perturbations of n plus 1/2 of the half integers. And they will get closer and closer as we go to infinity, because the L2 norm is small. Okay, so we got some information. We got that's our starting point. So we now check out which are the zeros. No, we can even, I mean, this is a fixed point argument. So we can implement the solution of this thing. We did implement it, and we get the zeros with high precision, 100 or 200 digits. So we got the zeros nailed down. And now you look at the zeros, and I claim that if you have the zeros, you have the function, because you have this product formula. But of course, this is very bad, because this product formula is converging very slowly. So you have to have the zeros to extremely high precision to identify the extremal function. Good. Then what you do? Then what you do is you collaborate with very smart people. So these are, and these, I can claim that some of my collaborators, in particular, this is due to Radchenko himself. He look at the zeros and he can say, oh, the third zero is there's a linear, it's an algebraic number in the first two zeros. And just by looking at the and the fourth one also, and the fifth one also. Well, this means that there should be some sort of recurrence relation. Well, that means that there should be some differential equation that governs this thing. And then you start to look for it and you find it. But there is some magic involved here. Okay, now I show you the solution of the problem. So the three main characters that are going to give the clue of how to identify the function are the following. First, there is the constant c, which is the c1. This is our initial object of desire. That is what we wanted to find out. Then we have another function, this constant L of 1. This is an L function of the zeros. So I just take the sum of the zeros with alternating signs. This is going to be convergent because it is very close to n, and we know that they behave like n. It's absolutely. And now we consider this other function phi. That's strange because this is no longer an even function. But this is, morally speaking, phi of 0, I'm taking half of the zeros of the solution. Tau n were the zeros of the extremal function, which were appearing in couples. And now I'm taking one from the right, one from the left, one from the right, one from the left, and so on. So therefore, I can write the solution as the product of this times this. It's phi of zeta, phi minus zeta. So morally speaking, this one is like the square root of this one. And we were minimizing some sort of L1 problem. So here we will be minimizing some sort of L2 problem that's easier to work with. So we express the solutions. So we will identify this function, capital phi. And of course, if we know this one, you agree with me that we know this one. So these are the three characters and everything on the statement. We found out some funny functions, some funny solutions for the constant c, some relation between the c and the zeros, which is not very useful because we don't know either the zeros or c, but they are related in this way, along the way. Okay, so these three characters we keep, and everything will be expressed in terms of this. And this is our main theorem, that the capital phi satisfies this second order differential equation. Note that the differential equation itself depends on the constant c and depends on this constant L of 1. These two constants are unknown. These depend on the, but they exist. So there are two constants, if you want, A and B, such that the F satisfies this differential equation. If phi satisfies this differential equation. And moreover, so this is one characterization, and this is another characterization. We prove that the capital phi satisfies a functional equation. So this sort of functional equation with the inverse, and and conversely, any entire function which solves either the differential equation or this one is a multiple of the original one. Okay, so this is I believe, a full solution of Hormander's program to identify the solution, because once you have this, I mean, now you can get all the information you want on the phi from the differential or the functional equation. For instance, okay, let me just first check out why this. For instance, I'm not going to present the proof, but I'm going to show you why a solution of this differential equation implies that we have a solution of the functional equation. This is due to some, this is, it may remind you of something which was done in the 60s in the Bell Labs, where they had this, what they call this serendipity accident. Well, that's what they were looking at, the eigenvectors of the concentration operator in the Pauli-Wiener space. These were these eigenvectors of this concentration operator. Well, they were very important in signal theory and communications because these are functions which are very well concentrated in time and space. And the solutions of this concentration operator, what they found is the serendipity as a Slepian, this is a work by Slepian, Landau, and Pollack. And the serendipity that they have is that there was a differential operator that commuted with the how do you call it? With the concentration operator. And if a differential operator commutes with this integral operator, they must have the same eigenfunctions. And this differential operator was the differential operator studied when studying the wave equation in an prolate spheroidal. Prolate spheroidal, this is something like a rugby ball. So you work in prolate coordinates and you solve the Laplace equation in these coordinates, and you get a differential operator. And this had been studied since the 19th century, which were the eigenfunctions and everything. You knew everything about them. And since they commuted with the other thing, you got the solutions of the bandwidth of the concentration operator by invoking the results on the prolate spheroidals. Okay, so certainly what happens here is that this is the differential operator that we have. It's of this type. What we have is that this differential operator, this is this piece of the differential operator that's only up to here. And what I'm saying is that we have this family of differential operators, and the theorem says that phi is an eigenfunction with this value of lambda and these values of the parameters. And now you check out that this differential operator commutes with these composition operators. You take f, you invert, you multiply by this exponential. This is a weighted composition operator. And you have this family of composition operators. So we have already our differential operators and some commuting composition operators. This means, well, what happens here is that, of course, if you have one solution to the equation, you can check that this composition is going to be also, you can get another solution of the differential equation. This other composition is going to be another solution of the differential. And you've got three different solutions of a second order differential equations. There must be some linear relationship, and this is the functional equation. Okay? So that's it's the fact that this commutes with this action. Good. So that's the way how we connect one with the other. Now, let's skip this part, the sketch of the proof of the differential equation. And now I get into the consequences. Of course, I can find out from the differential equations, I can find out a recurrence relationship for the Taylor expansion. We know it has a Taylor expansion. You just plug it in, and you get a full Taylor expansion of our solution. It will be written in terms of L of 1 and C. So these two constants determine everything, and I get the full Taylor expansion. And I can also get from phi the real minimizer, phi of zeta, which is capital phi of zeta times capital phi of minus zeta, and you have this Taylor expansion. I brought just the first terms. You see, they are always polynomial in C and in L of 1. And you can also get a third order ordinary differential equation for phi itself from the equation. So this is the equation that the solution of the minimasser must satisfy. It's also an equation which is a linear differential equation. Good. So this is some consequences. And from the functional equation, we solve some of the problems that Hormander and Berghanson posed. Well, what they did, I did not tell you, what Hormander and Berghanson did is, okay, let's pretend that we know the Fourier transform. Well, the Fourier transform, it's going to be something that the picture is going to be some function here. That's well, let's pretend that I even, and in minus pi or minus 1, 1 in this convention. So it's going to be some function like this. So they just write it down as a linear combination. So here, well, it may be even, there were only even powers. 1 minus zeta square. That's wrong here. Yeah, no, that's correct. So it's going to be something of this type. They just look at something like this. So they were looking at functions of this type, and they were determining which was the coefficients AM that minimize the corresponding problem. And that's how they got this numerical approximation. And they checked that, well, the solutions that they got, maybe they just got it up to 6. So they found out, so this is going to be approximation of something. And they found out that these coefficients decay very quickly. And they claim, well, that they couldn't check. They suggested that this function, the Fourier transform, was an analytic function, by the way this decreasing this, but they couldn't even prove that it was infinity function. But now we can just we can prove that this is indeed an entire function, and this is just an immediate application of the functional equation and we know more or less the growth of the coefficients because we know the order of this entire function. So really, they were right. I mean, their guess was correct. Well, everything boils down to getting this C now and L of 1 correct. And this you can do by using some spectrum theory. You can, in the Fourier side, the differential equation, or if you want, it gives you rise to another differential operator, but now on the Fourier side. And this is a perturbation of the Legendre operator. And now we write this in this basis of Legendre basis, and we can study very precisely the structure of this differential operator. And this allows us to get the constant to very high precision. So this is C, and this is L of 1. And with this, we can get as many digits as we want with very shortly. Now, let me just finish with this thing. We have here, we associated to the zeros of this phi1 function, these Dirichlet series, no? These L functions, this other L function, and it has properties which are reminiscent of the classical L functions. In particular, I want you to point out to this this particular sum here. Here, you should recognize here the Basel formula, where this sum, the sum of 1 over the integers squared gives you pi. And here you have the Leibniz formula, you can write pi on the, so here we've got the same formula that gives you pi in terms of the integers, this way and this way, but here the role of the integers is replaced by the zeros of this phi function, and the role of pi is replaced by this constant. So I find it amusing. And maybe there is more structure to it than we know. Some open problems. Well, we don't know why the commutation relation holds. We suspect that this is going to be decreasing. And the extremal function, we don't know whether it's unique in the non-convex setting. This thing. And I would like to advertise this. Can I have 1 minute? Just so to advertise this problem, the one in P equal 4. If you look at the Euler-Lagrange equation, it looks the Euler-Lagrange equation, the equivalent, our starting point here is that if you have this minus 1, 1, you have this function here, f, which is here, the Euler-Lagrange equation that will give you, this is the Fourier transform of the Pauli-Wheeler function. The Euler-Lagrange should be that f convolved with f convolved with f should be identically, this is a function supported in minus 3, 3, well, that's -3, that's +3. So this is going to be some function here that should be constant equal to 1 here. So the problem is to find a function f, little f, here, such that f convolved with f convolved with f is equal to 1 in this interval. Find it. Find it, I mean, there are numerical experiments. This is doable. There are things, but I would like, maybe this thing should be something of, it's very close to 1 over minus the square root of x squared, and it should be something of this type. So prove that there is a solution of this type to this equation, and this will solve the Venn-Green problem. Okay, stop here.